Hello, dear audience. My name is Luis Enrique Alvarado Vargas, and today I will be presenting the poster titled Growth and Optoelectronic Behavior of Magnesium Doped Zinc Oxide Thin Films for DSSCs. This work focuses on the development of an efficient and low-cost method for producing magnesium doped zinc oxide thin films and evaluating their potential as photoanodes for dye-sensitized solar cells, also known as DSSCs. The methodology involves chemical band deposition, which allows film growth at temperatures below 100 degrees Celsius, followed by a post-deposition thermal treatment to ensure the electrical and mechanical stability of the resulting films. The process, depicted in Figure 1, begins by weighting the precursor materials zinc acetate and magnesium chloride, based on stoichiometric calculations, to create the precursor solutions. Next, the magnesium doped zinc oxide precursor solutions are prepared, with magnesium atomic concentrations of 0, 1, and 2 atomic percent. Then the volume of magnesium doped zinc oxide precursor solutions are distributed among the number of samples, and the substrates are immersed in their corresponding solutions. The samples are then placed in a thermal bath at 90 degrees Celsius for 2 hours. After this, the substrates are removed from the solution and a thermal treatment is applied at temperatures of 300, 350, and 400 degrees Celsius for 1 hour. This step allows the variation in temperature for each magnesium concentration. This study systematically explores the relationship between the amount of magnesium dopant, the thermal treatment temperature, and the optical and electrical properties of the samples. Specifically, magnesium doped zinc oxide films with 0, 1, and 2 atomic percent of magnesium subjected to annealing at 300, 350, and 400 degrees Celsius. The optical characterization was performed using ultraviolet visible reflectance spectroscopy, confirming the successful incorporation of magnesium into the zinc oxide lattice. The doping effectively tuned the bandgap values of the films. All samples exhibit strong ultraviolet absorption and high transparency in the visible spectrum, which is a critical characteristic for DSSC photoanode. Findings from the 4-point probe analysis of sheet resistance established a direct correlation between sheet resistance, magnesium doping concentration, and annealing temperature. A lower sheet resistance is highly desirable for an effective DSSC blocking layer, as low resistivity can lead to an increased maximum voltage and a higher overall efficiency. The optimal electrical parameters were achieved with the undoped samples, 0 atomic percent magnesium, which demonstrated the lowest sheet resistant values at annealing temperatures of 300 and 400 degrees Celsius. In conclusion, this study validates a low-temperature chemical band deposition process for the fabrication of zinc oxide-based thin films suitable for DSSC photoanodes. The undoped zinc oxide films annealed at 300 and 400 degrees Celsius were identified as the most promising candidates. Their combination of high transmittance, low resistivity, and well-matched bandgap makes them ideal for an effective DSSC blocking layer, confirming the viability of this low-cost manufacturing approach. And with this concludes my presentation. Thank you very much for your time, and I invite you to reach out if you require any further information on this research.